Can you hear me? Clear? Oh, not yet. No, it's a little bit up. Right. So, they are put it a bit up. No? All right.
No, that will be uncomfortable
Okay,
for you.
yeah,
I can
comfortable.
once we close the door, it will be fine.
Yeah, how is this? This is good. This is good. Yes, yeah, very straight transition. Yeah. Probably I was looking for positions at that time. So I joined in 97, 97 January. And Syracuse, Utah, back to. All good. I'm sorry to hear. Yeah, yeah. Okay, so you can start. Sure. Yeah, but
let me welcome all of you to today's talk on quantum gravity, the quest for the quantum mechanics of space and time. So this is part of our International Year of Quantum celebration, and the speaker is Professor Madhavan Varadarajan from the Raman Research Institute, and I have known him for a long time, 30 years, I would say. So Professor Varadarajan did his PhD at Syracuse with, yeah, Syracuse. I think the last part was at Penn State, but that was with Professor Ashtekar. And I remember talking to him about his PhD thesis, which obviously is very interesting. Anything in quantum gravity is very fascinating. Then he did his postdoc at the University of Utah, Salt Lake, and with Carl Kokesh. Yeah. So it was a very well-known, general relativist. I didn't know that he was working on quantum mechanics. On quantum gravity, but I knew of him because of his reputation in the field of general relativity. And he's been at Raman Research Institute since 1997 and continued to work on various aspects of quantum gravity, in particular loop quantum gravity, and he's undoubtedly the leader in India in that field, and you will get to hear from him about quantum gravity and maybe aspects of loop quantum gravity also.
Maybe a little bit,
Maybe a little bit.
very little.
So with these few words, I would like to invite Mr. Varadarajan to give his talk.
Yeah, I think I've got this. So. Yeah, thanks, Manu. Thanks a lot for inviting me here. I understand it was quite a tricky time because lots of meetings and so on. And Siddharth and I had a lot of correspondence. I guess he's not well, not here, but thanks to him and thanks a lot for having me here. It's a um, I, I wish I had come with a
Professor,
little bit more time, but already the couple of 2, 3 people I've met are very inspiring, and I even got to see a qubit today, which I've never seen in my life. So that was absolutely amazing. Um, uh, and yeah, I had a great conversation with Pankaj in the morning. So yeah, I would second Pankaj's request. Relax, it's just going to be fun. So if you just, you can come here and like enjoy the talk a little bit more if you come up in front, and just feel free to ask me questions because I know this is a mixed audience, and the interests over here might be completely different. So I would like to tell you a little bit about the field of research in which I work, which is quantum gravity. So what is gravity? Quantum gravity is a yet incomplete effort to find a quantum mechanical description of the gravitational interaction. Now, all non-gravitational interactions, such as say the strong nuclear force, the weak nuclear force, or electromagnetism, so all these interactions we know how to describe in quantum mechanical terms. And indeed, this is really what underlies the standard model of particle physics. Gravity, however, is proven to be a tough nut to crack, and we still don't know how to provide a quantum mechanical description to gravity. And the reason is that gravity is very peculiar. It's very different from other interactions. And what I'd like to do in this talk is to tell you why it is so different, and what are the conceptual and technical difficulties in trying to construct a theory of quantum gravity. And I will be speaking from the perspective of someone who is trained in general relativity. And general relativity identifies gravitation with, as we shall see, the geometry of space-time. So the quest for the theory of quantum gravity is then nothing but a quest for the theory of a quantum mechanical theory of space and time itself. So that is why I have that title. Let me tell you what the plan of the talk is. So first, I'll say a little bit about classical gravity. And the main takeaway message from this part of the talk is that classical gravity is really a theory of space-time itself, and it is not a theory which unfolds in a given space-time. And this is actually, as we shall see, why there are, this is the heart of all the conceptual and other difficulties which come about when one tries to think of a theory of quantum gravity. Next, I will just estimate for you when quantum gravitational effects are expected to be significant. And we shall see that they are expected to be significant at unimaginably small distance scales or unimaginably large energy scales, which are not going to be directly accessible to any accelerators on Earth. So there is a legitimate question which any quantum gravitational practitioner is asked, which is why then are you worried about this? Because there is practically, there is no direct way to test this. So there are certain theoretical reasons which are very interesting and which I will dwell on a little bit. And this will involve then saying a little bit about the Big Bang and the structure of black holes and their very curious properties. After that, I will return to the question of contact with observations. And even though it is very difficult, people are really trying in some indirect way to see whether they can probe quantum gravity. Then I'll just give you a laundry list of approaches to quantum gravity. And then if there is time, I'll say a little bit about loop quantum gravity. So please stop me if you have questions and if I'm assuming much. And please tell me to go faster if I'm saying something which you already know very well. Okay, so let me say a few words about classical gravity. Now, for most terrestrial and in fact most astrophysical purposes, Newton's theory of gravity is adequate and satisfactory, and that's what people use most of the time. However, if one wants to look at very, very strong gravitational fields, like at the beginning of our universe or deep inside black holes, etc., or if one wants to look at extremely accurate measurements of weak gravitational fields, then Einstein's theory is really the correct theory. For astrophysical and terrestrial purposes, there's not much to distinguish practically. Of course, Einstein's theory reduces in its calculation of effects exactly to Newton's theory. However, even there is a very profound change in perspective. So, I mean, this is, as you must have seen in lots of popular science expositions, if you look at, for example, the gravitational interaction between the sun and the earth, right? So the Newton would tell you that the sun is a massive body, it exerts a gravitational force on the earth, and therefore the earth, instead of traveling in a straight rectilinear motion, is pulled into a curved trajectory which then orbits the sun. What Einstein would tell you is that no, this is a wrong picture. There is no such thing as a gravitational force. The sun, by virtue of its mass, distorts the space-time structure in its vicinity. It curves the space-time structure in its vicinity, and the Earth tries to move as straight as possible on this curved space-time. And because the space-time itself is curved, one perceives that the Earth is moving in a curved trajectory, right? So these are two completely different perspectives which give you quantitatively the same results for weak gravitational fields, but Einstein's theory has corrections. And since this is really the theory of gravity, this is the theory which we are going to base our quantum mechanics on. We would like to construct a quantum theory of Einstein's theory of general relativity. So before going to any discussion of quantum mechanics, let's try and understand what the mathematical object is. Just like in Newtonian physics, you know, the mathematical objects are the position, momentum of particles, and so on and so forth. Here, what is the mathematical object which characterizes the fundamental degree of freedom, which is the geometry? Right? That is what we want to describe. And that is, whatever object that is what will be then occurring in Einstein's description of gravity. So in order to characterize the geometry of anything, the answer turns out to be that the mathematical object which characterizes geometry is the distance between a point and its nearby points. Okay, so let me take the example not of space-time, but just of space, and that to two-dimensional space, like the surface of this table, right? Now, clearly, if I take a point here and I take a point very close by, right? So let's say that we have these Cartesian coordinates x and y. So if I look at point x, y, and another point close by with x plus dx and y plus dy, then you know that usual Euclidean geometry by Pythagoras' expression just tells you that the distance between these 2 points, the distance square, is just dx square plus dy whole square. Fine. Not But what is nice is that one can invert this whole thing, right? So supposing somebody gave you a plane worth of points. Okay, so just bunch of points which are labeled by x and y, right? Two coordinates for each point, but I'm not telling you what the distance is between these points. And suppose I tell you that you place these points in such a way that the distance between two nearby points is exactly that. So these are labels. Each point has a label. I just assemble them, and I want to assemble them in such a way that the distance between 2 points is exactly that distance which we wrote down on the previous page. And what you will find is that the emergent geometry, when you do this, is exactly that of the plane. The points will arrange themselves in a flat planar geometry. Okay, so therefore, it is really this distance function which completely determines the geometry. Geometry determines the distance function determines the geometry. Let's do a slightly more non-trivial example, which is, that of the round sphere. Yes. I'm now, no, that would be, let me finish, right? I'm not doing r theta here. This is theta and phi. Okay, so let me now look at the surface of a sphere, right? A round sphere, a round football. And one can coordinatize these points on something which has the topology of a sphere with angles, theta and phi, right? And if you want to get more technical, then you need two charts, etc. I won't get into all this, but roughly speaking, you can take a sphere worth of points, like we took a plane worth of points. Again, I don't tell you the distances between them. I give them their labels, theta and phi, and I ask you to arrange these points in such a way that that the distance between 2 points is exactly, is there a laser the center? Anyway, so if I ask that these points be placed in such a way that the distance between them is this thing over here with some capital R, then again you will find that these points will be spaced not on a squished sphere, but actually on a perfectly round sphere. Okay? So by giving you the distance function between two nearby points, once again, what will emerge is the geometry of the round sphere, right? And of course, if you had a round sphere, this would be the distance function. Okay, is that clear? Good. So now let's go from two-dimensional space to space-time. So that the geometry of space-time also can be completely specified, and this is just a higher dimensional version of what we talked about. And if you give me the space-time distance from any point to all nearby, then again, it turns out that this specifies the geometry completely. For example, in special relativity, this distance is, it looks between, so let's take a point with inertial coordinates x, y, z, and t, and a nearby point with inertial coordinates x plus dx, y plus dy, z plus dz, and t plus dt, right? Then in special relativity, the distance between these points is given exactly by this expression over here. And this looks as though it's just the distance in space, and the time comes with a minus sign over here, right? So what that means is that if the temporal separation between two events dominates the spatial separation, then this distance can be negative, right? This distance square can be negative. It can also be zero, right? And when is it zero? When the temporal interval is exactly, this is the velocity of light, so c times that interval is exactly equal to the spatial distance, right? And so that means exactly that these 2 points can be connected by a light ray, right? Because the distance is equal to c times the time. So those, but in that case, the distance between these things will just be zero, because this will cancel this, and therefore it's a light, these distances are called light-like. Or it can be that the spatial part, the spatial separation dominates the temporal separation, in which case the distances are positive and are called space-like. Now, one can do the same exercise, right? So I can give you a 4-dimension worth of points labeled by x, y, z, and t, and I can ask you to place these points in a geometry, a 4-dimensional geometry, which we can't really picture or imagine, but mathematically in a 4-dimensional geometry where the distance between nearby points is given precisely by this. And then in a technical, mathematically precise way, you will find that the geometry which emerges is flat. It has curvature at all in this 4-dimensional sense. And this gives you back the geometry exactly of special relativity. So this is what an important characterization of special relativistic geometry is. Supposing I'm sitting, I just suppress the z because I can't draw it over here, so that 2 space and 1 time, x and y and t, these are the inertial coordinates. I'm sitting at some point x, y, t over here. And clearly, when I shoot light rays out, right? When I shoot light rays out over here, they're traveling at the speed of light, and so the c delta t is exactly equal to the delta of the spatial distance, right? So that's why they're traveling on along light rays. And this is, since you can go in any direction over here, this traces out a cone, which is called the light cone, right? So you can go shine light to the future, you have the future light cone, and light can come to you from the past, and that's the past light cone. Now, if you look inside the light cone, right, points inside the light cone are such that the temporal separation between, for example, over here, there is no spatial separation at all, it's only time, but everywhere inside the light cone, the temporal separation between a point over here and the point over here dominates the spatial separation. So all distances from points from here to here are time-like. And that when the temporal separation dominates the spatial separation, then it takes more time to reach that point than it would have from a light ray. So these are all which are accessible through signals, which travel less than the speed of light. And similarly, points from the past over here in the past light cone are those which can send signals to this point over here. If you look at points outside, then in order to send a signal here, you would have to travel at a speed which is much greater than that of the velocity of light. And so you cannot have any signals which either reach you from any points outside to here, or you cannot also send signals from this point to any point over there. Okay. So what this diagram says to you is that once you give me the geometry of space-time, you also simultaneously infer which events can influence which events and which events are capable of influencing a given event. And this is called the causal structure of the space-time. So geometry determines causal structure as well. Now, what happens in general relativity? In general relativity, it turns out that the network of distances between pairs of nearby points in space-time can constitute a curved geometry, right? So I can specify these distances in such a way that the emergent geometry is actually curved. And nearby points, it turns out, are still going to be either time-like, space-like, or light-like separated. Okay. So if you want to know whether a signal is actually a physical signal, then you have to go to any part of that signal and just see whether locally the distance between 2 points on that trajectory are time-like related or light-like related, then that will be the trajectory of some signal. So nearby points can be time-like, space-like, or light-like separated, and once again, which points can influence which other points is determined by the geometry itself. So causal structure, once again, in general relativity is also a part of the geometry. Now, it might seem maybe a little bit sort of too abstract, and but and sort of, maybe 20 years ago, I would not be able to give you an example of general relativity in your daily life, but now there is an example, and you're constantly using it, right? So this is just the GPS in your smartphone. So why does general relativity, why is it so crucial to the functioning of the GPS? I mean, if you did not know general relativity and did not accommodate for it, then it turns out that, you would not be able to really use the GPS in any reasonable way. So what underlies that? So the first thing to notice is that if you take a clock and you look at the duration between two ticks of a clock, right? The clock is not moving in space. It's at the same spatial location. So that distance in space-time is a time-like distance, okay? Because the time separation dominates the space separation. Now, all time-like, space-like distances and their geometry are dictated by how the space-time geometry is curved, right? Which in turn is dictated by how much matter there is, right? Like we said in the beginning, if the sun is a huge object, massive object, it curves the space-time around it. So similarly, if you have a clock on Earth, near Earth, Earth has curved the space-time, right? And a clock ticks in a certain way. If you go far away from Earth, right, say on a satellite, then it turns out the clock is going to tick slower than the clock has been ticking on Earth, because the gravitational field of the Earth, or the curvature away from the Earth, is much lower than the curvature on Earth. And it's lower by a very, very little amount once you write it down in appropriate units. But nevertheless, it is true that there is a difference in the rate of ticking of clocks on satellites and on Earth. Yeah. 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 Yeah, there will be tilting of light cones, and this will play a very, very important role. That's a wonderful question, and we'll see it more. The most dramatic instance of this is around a black hole. Okay, and we'll come to that in a little bit. Okay, so now what has all this got to do with the GPS? Well, what is the GPS? Your phone is a receiver, right? And it receives pulses from a minimum of 4 satellites in the sky. So the satellites send pulses. They're constantly sending pulses here and there, and you're the receiver, and you receive 4 of these pulses at your same space-time point, right? So your unknown space-time point, x, y, z, t, receives these signals, right, at the same time t and at the location x, y, z, right? And we don't know what this is. The satellites send time-stamped signals with information about their location at the time at which the signals were sent. And you can do a calculation then by looking at the geometry, etc., and you can take these 4 streams of known data and invert them and solve for x, y, z, and t, your 4 space-time coordinates. Okay, so that is an idealized way in how this GPS works. But in order to actually make this calculation work, you need to be able to know exactly what the relation is, all in terms of time, right? Pulses are sent at some time in the satellite clocks, and they come to you over here at the same time. And you have to find a way in which to convert the time which is measured on the satellite to the time over here in order to do this calculation. Because the satellite is away from you and is not on Earth, it turns out that there is a difference in a minute of ticking over here of a few nanoseconds between the satellite. And so when Earth ticks a minute, then up to a few nanoseconds they agree, but it's important, right, that this doesn't, that there is this difference. And if you do not feed in this difference, then the GPS would just very soon give you wrong information about your position. So in a matter of 30 minutes or so, for civilian purposes, and they have a different code for military purposes. In a matter of minutes, because they need to be much more accurate, the GPS would stop functioning, right? So, and I mean, basically, where does this minutes and so on come from? It's just nanoseconds, and the operative thing is the velocity of light. So you multiply the two, you will get like a few centimeters, and then you put it in a few minutes or 30 minutes, and then you will get 5, 10, 15 meters, and then soon you will be out of, you will not be able to determine your position accurately. So each time you use your GPS, you should realize that what is called the gravitational redshift, the fact that time itself manifests differently here and over there due to the curved space-time geometry, is real. Okay, it's not just some abstract mathematics, but it is actually real. And if you did not account for it, you would be lost, say in your car or etc. etc. This GPS would just simply not work. In fact, when the engineers first went and tried to construct this, they just did this by hand, this correction. They did not know why things were not synchronizing, why things were failing, and the actual reason is because of the gravitational redshift. Okay, so I hope to have convinced you that the curvature of space-time is a real thing, right? It affects time, it affects space, and general relativity is actually a physical theory. So let us now come slowly to quantum gravity. So let us do a thought experiment, right? And let us first switch off the gravitational field. Okay, so just by hand, let's switch off the gravitational field. So there is no gravity at all. Then the space-time is really the flat space-time or special relativity, right? There is no curvature, everything is fine. The dynamics of matter and light and all their quantum fluctuations unfold in this fixed space-time arena, which happens to be flat. Now, let us switch on classical gravity. So, of course, what happens now is that space-time curves, right? It's no longer flat, it curves. Light cones kind of twirl around a little bit, but everything is a fixed structure. And on this fixed space-time structure, once again, you can look at quantum matter fields, right? And their evolution, their fluctuations. Nothing conceptually has really changed. There's it's technically harder to do quantum mechanics on a curved space-time than on a flat space-time, but conceptually, there is really no change in your conceptual setting. But now, let us switch on not only classical gravity, but let us switch on quantum gravity. So when you switch on quantum gravity, the basic variable is this grid of spatio-temporal separations, right? The metric. So the metric starts to fluctuate, right? Because in quantum mechanics, your dynamical variable fluctuates, right? So the metric starts to fluctuate, and you no longer can deal with a fixed stage on which everything unfolds, because your light cones become fuzzy, right? Your distances are subject to quantum fluctuation. Yeah, your sense of time is subject to quantum fluctuation, what the temporal distance is. And in some sense, what we had earlier was a fixed stage, and all these other particle physics, etc., they were just actors on that stage. Everything was unfolding there. But now what has happened is that the stage has come and joined the actors in this whole play. So everything has become very, very confused and blurred, right? And finally, I mean, at this stage, right, even what causality is not very clear, right? Because the light cones themselves are fluctuating, and what is, was connected by a light ray or not, etc. Everything is subject to quantum fluctuations. And indeed, at the very basic conceptual level, classical space-time itself completely loses its meaning. Just like in quantum mechanics, right? The notion of a particle trajectory loses its meaning, because you cannot simultaneously say what the position and momentum is. Here, because of quantum fluctuations, classical space-time just loses its meaning, right? So then what do you do, right? You have to construct a quantum mechanics of space-time itself rather than a quantum mechanics space-time, okay? And if you've been following me till now, then I mean, you should kind of, yeah, I don't know. Depending on how closely and intensely you've been following me, your head should be going round and round because, I mean, what do you do, right? You just don't know. I mean, any experience you have with quantum mechanics or quantum field theory is always on a fixed space-time. And when that also starts to fluctuate, when causality fluctuates, light cones fluctuate, distances fluctuate, what the hell are you doing, right? We don't know. And this is really the principal conceptual difficulty in quantum gravity, and that is why it is so hard to even get started. Okay, good. Yeah. Yes. That is, yeah, there will be quantum fluctuations. That's all we can say, right? And it depends on how then you actually set up your quantum theory of gravity to really understand what these quantum fluctuations are. They will obviously, they will depend on the quantum state of the gravitational field, right? How these things fluctuate or don't fluctuate, so everything is up for grabs, right? We don't know. So right, so we really don't know, and that is the whole problem. Right, that's all we know, and this is what I'm trying to point to is why gravity is so different from other interactions and why it is therefore so hard to address the problem of quantum gravity. Okay, that is the whole reason why we've gone through this exercise to really tell you that yes, I mean your guess is as good as mine conceptually, right? Because we just don't know. Okay, so now I hope I've convinced you that this is a very, very confusing problem. We can now estimate as to when quantum gravitational effects are going to be important. At what energy scales does it is the gravitational field really, really going to fluctuate, right? At what energy and distance scales or time scales? Now, just as a rough back of the envelope calculation, you notice that in the classical theory of general relativity, because it is a relativistic, the velocity of light is one of the constants which occur in the dynamical equations of the theory. And because it's a generalization of Newtonian gravity, Newton's constant also occurs in Einstein's theory of general relativity. On the other hand, quantum mechanics is characterized by h bar. And so if you put these three-dimensional constants together in different ways, then you get objects which have the units of length, time, energy, etc., right? And these are called Planck length, Planck time, Planck energy, and so on. So the Planck length is unimaginably small, right? Nuclear size is a femtometer or so, maybe 10 to the minus 14. And this is 10 to the minus 35 meters. It is unimaginably small. A Planck time is 10 to the minus 44 seconds, right? So it's all science fiction. I mean, you cannot even conceive of how small these numbers are. And the Planck energy is huge. It's around 10 to the 16 times the energy of the LHC, right? 16 orders of magnitude. So you can just give up, right? You are not going to be able to build an accelerator which is ever going to reach these energies at all, right? One is now really struggling to go to the next thing after the LHC. So, I mean, if they're just so unimaginably away from our even particle physics kind of experiments, then why are we worried about this thing, right? We can never test it directly. So why just, and a lot of physicists for a long time would say, worry, I mean, you're doing metaphysics, you're really not doing physics. And that criticism is still, people still say that. So let me give you a couple of reasons as to why it is a good idea to look for a theory of quantum gravity. The first reason, and these are both theoretical reasons, but they're very interesting reasons, right? So the first reason is that of singularity, right? So what is a singularity? If you look at, we had Newton's equations earlier, right, which said that you give me a matter distribution, I can calculate what the gravitational field is, and I can calculate how particles move in this gravitational field. What replaces that is the Einstein equations, which is a more covariant version. So instead of the gravitational force, on the left-hand side, you have the curvature of space-time, right? So you have the metric, and there's a mathematical way of computing its curvature. So the curvature resides on the left-hand side, and on the right-hand side, instead of the mass, you have something more covariant, which is the energy momentum tensor of the matter. Right? So you have energy momentum tensor equals the curvature with some Newton's constant, velocity of light, etc. And you solve these equations. So you have matter fields and you have the metric, and you solve these equations. And the solution of these equations is a single curved space-time with matter which is propagating on the space-time and simultaneously and self-consistently curving the space-time on which it is propagating. Okay? So that is what a solution to the Einstein equations is. Now, we can look at particular solutions of these equations. So let us do so. If we look at our universe at large scale, right, cosmological scale, then the universe looks extremely homogeneous and isotropic. So if I look out in this direction or look out in that direction or this point or that, the geometry looks exactly the same. The geometry is homogeneous and isotropic at very, very large distance scales, which means going back in time, right? Because that light takes time to come to us. So you look very, very early and you look at very large distance scales, cosmological distance scales, and you find that basically the space-time is homogeneous and isotropic, right? So you take that homogeneous and isotropic space-time, right? And you evolve it through the Einstein equations, you evolve it backwards. Yeah. Yeah. Yes. Yes. Right. Right. So yeah, that's a cosmological question and this has to do with the distance ladder, right? And how, so that's a different, you're asking observationally, how do we know that we are looking at large distance scales, right? That is the question. So firstly, how do we know we're looking at large distance scales? And that involves this whole astrophysical distance ladder, which is a separate discussion, which, I mean, I'm also not an astrophysicist, but each time I have to read it and tell you what it is. And then once you look at large distance scales, right, extra super galactic distance scales, then you see that basically, the world actually does look at those distance scales, everything does look uniform. So that's a statement of physical observational fact. It's not clear. I don't know how much Lemaitre and Friedman and I mean, I don't know. I know it's not so clear. I don't know because it wasn't that things were. I mean, Hubble came later. That is true, but it's not clear to me. I don't know. I don't know. It's not clear that there was no. I'm would have to look into the history of those. I mean, things happen fairly rapidly, right? So. Um, but I wouldn't be able to trace the history. I'd have to read it up and tell you. So this is but certainly with modern observations, this is true. And if you take the geometry at those cosmological scales, right, and you evolve the geometry backwards using the Einstein equations back in time, then you find that the space-time curvature is increasing, right? And in that sense, there is a contraction. And you go back in time, and then in a precise sense, a finite time earlier, the space-time curvature blows up. The densities, matter densities blow up, and that time is the Big Bang. So that is when space and time actually came into being, right? So it's not a Big Bang in space and time, it is a Big Bang of space-time. That is when space and time came into being, and that is when this whole thing started, right? So that is the classical general relativistic description of homogeneous and isotropic cosmology. But of course, you see, when the curvature blows up and when things blow up, then you don't know, your equations break down. And generally in physics, when your equations break down, this does not mean that the physics is broken down. It's just that the domain of validity of your equations is now surpassed, right? So you cannot, you can't do classical mechanics at the angstrom level. You'll have to put in quantum mechanics, right? So at some point, your physical theory is going to break down. And for example, and in fact, that's a very good example. If you took the hydrogen atom, right, with a proton and an electron moving around it, and you did classical theory over there, right, just electrodynamics, then the electron would radiate. It's accelerating and it would fall in, and we wouldn't be here, right? So the thing which stabilizes the atom is really quantum mechanics, right? This solidity of this, our existence, everything is because of quantum mechanics. Some strange way which quantum mechanics, a new theory comes in, subsumes the old one, right? So similarly here, before the curvatures blow up, the curvatures, they have 1 over distance square, that is the unit of curvature. So before that blows up, it is going to go to 1 over 10 to the minus whole square, which is the 1 over Planck length whole square, right? Before the energy densities blow up, again, they will go to Planckian energy density. And at that stage, you would expect that quantum gravitational effects are going to be important. So one very important physical reason to study quantum gravity is to ask whether quantum gravitational effects can provide a completion of your theory. Can they ameliorate the singularities of the classical theory, right? Much like in the case of the hydrogen atom, which we just discussed, quantum mechanics actually gives you a satisfactory description of the hydrogen atom where classical theory could not. So similarly, maybe a quantum theory of gravity can help you go past what was the classical singularity, right, and cure it. So the question is, well, does it do that or not? And in order to answer this question, you have to come up with quantum gravity. So that is one reason to study quantum gravity. Another, yes, 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 yes. It's a question, right? Because you believe that, I mean, if you believe that physics is good and there has to be, a good physical description, then there is a natural candidate for what could ameliorate the singularity, and that natural candidate is quantum gravity. So this is a good reason to try and construct a theory of quantum gravity and ask whether this happens or what happens. Okay? Remember, we are just looking, I'm just trying to convince you that trying to look for a quantum theory of gravity as a physicist is not a completely bizarre idea, even though the distance scales and energy scales are so humongous, right? I mean, distance scales are so small, energy scales are so big. A second reason to study quantum gravity is black holes. Okay, and again, I don't mean by this, the astrophysical properties of black holes, the accretion disks and all that. No, I mean the mathematical properties of black holes as solutions to the Einstein equations, and it will become clear in a moment. So, in general relativity, as in special relativity, the speed of propagation is limited by that of light. So, locally, you can only go along the local light cone. Now, if there is an interior region of space-time such that even light cannot escape it to the outside, then so what happens is that stuff can fall in, but you can never escape, right? No signals can. So it's a hole, and because even light cannot go out, it is black, and that's why these things are called black holes. Now, these are just configurations of space-time metrics which are curved enough that this happens. The question is, can you actually find such solutions to the Einstein equations or not? And the answer is yes. There are solutions to the Einstein equations with exactly such behavior, and these are the black hole solutions, right? And unfortunately, I don't have time. I mean, there was another talk I could have given, which is about the history of, this was the first solution to the Einstein equations, which was found, Einstein published his 1915, okay? And the solution was found within a few weeks of his final theory, which he took more than a decade to come out with. And the discovery of that solution is extremely inspiring and wonderful. And I don't have time to tell you now, but maybe if you have somebody remembers and wants to know about it more, it's a absolutely fascinating story, which I would love to tell you, but maybe after the talk. Okay? And it truly is an inspiring, it's really inspiring story. But let us come back. So what is a black hole? Let me draw a picture. So now, actually, again, I can't draw in 4 dimensions, right? So I'm drawing in 2 plus 1 dimensions, and the circles over here are supposed to be spheres. So let's look at spherically symmetric black hole and suppress 1 dimension. Imagine that, you know, these circles actually spheres, surface of 2-dimensional spheres. And let's look at what light, you know, I said a black hole is something where even light cannot come. So let's look at what the structure of the trajectories of light rays are as we in a black hole solution. Now, if we go far away, right, from the black hole, then it's like in normal space-time. So what happens in normal space-time? Like in this room. In this room, if you take a sphere, an imaginary sphere, right, and I put people on the surface of the sphere, right, I ask them to shine light rays normal to the sphere. Okay, so they can shine light rays inwards or they can shine light rays outwards. The outward set of light rays will diverge, right? The wavefronts will go on increasing in size, they will diverge. The ones inside will converge. Okay, and that's exactly what is happening over here. You see, these light rays are going out. They're escaping out to infinity. These light rays in the inside ones are converging, right? And remember, this is a circle. This is the future. So it's exactly what I'm saying. Imagine it's a two-sphere, outward and inward. Inward is converging, outward is diverging. Now what happens is exactly what you said, right? Because the space-time is curved, the light cone over here, right, starts tipping. Okay, so the light cone itself, due to the curvature, starts tipping inside. And if you look inside, the light, sorry. If you look over here, the light cone is completely tipped here. So if you, the light rays here and here are here and here, and both sets of light rays are only going inside. That red line is the singularity, similar to the black hole singularity where everything blew up. Here, there is a central singularity in the black hole. Okay, is that clear? Is the geometry of the picture clear? If you look at that light cone, right, and you're inside the light cone, all your trajectories are on the surface, everything is going to fall inside the singularity. Okay. Now, as you're coming in and you're tipping over here, there will come a stage, right, where your ingoing light rays are still converging. Your outgoing light rays, little bit outside, were diverging, but right at this point are neither converging nor diverging. They just collimated. Okay, so they just stay there. They just hover. They neither make it to the outside to infinity, nor do they fall inside. And that set of last light rays, which just about hover, don't make it out, don't make it in, the last set of those outgoing, so-called outgoing light rays, traces what is called the horizon of the black hole. All right. And now remember, the horizon, this is a circle which was actually supposed to be a two-sphere. So the structure of the horizon is that it's a three-dimensional object which has the topology of a two-sphere times the real line, and which is traced by these light rays, which are neither expanding nor are they contracting, the light fronts. Okay. Now, as you will see, you see this, what can happen so it's a global thing, right? The light cones which are there can tip ever so slightly, right, as you go. If they tip very drastically, that means the curvature is high. Okay, but they can also just tip very slightly, and you can still get that structure. So large mass black holes at the horizon, they don't have very strong gravitational tidal forces. Okay, small mass black holes, turns out they do. So when one says, oh, the gravitational field is, or the forces are so strong that even light cannot escape, that is really not correct, right? It is a global phenomenon which involves the curvature. And the gradual tipping of light cones is as good as the sharp tipping of light cones. There has to be a division where some light is just trapped, and that light is inside over here. Okay, so that is a geometry which I spent a little time on. Now, as I said, the event, this is called the event horizon. The event horizon is three-dimensional with two-dimensional cross sections, which are spheres. Now, you know the space-time geometry, you know the metric, so you can compute all geometrical quantities, and in particular, you can compute the area of these two spheres. Let me give you some number, right? The area of these two, any cross section, you can compute its area. Now, we have been discussing geometry, we have been discussing metrics, we have been discussing gravity. It turns out that the area of these cross sections has a connection to completely different subject of thermodynamics. Okay, this is totally bizarre, right? I mean, I've not said a word about thermodynamics, and suddenly I'm going to tell you that there is a connection between this completely geometrical object and thermodynamics, right? So let's see what that is. Let me just review the concept of entropy. I'm sure everyone knows it, but maybe in more colloquial language, I can just tell you what it is. So entropy is a central concept, right, in thermodynamics, and in statistical mechanics, we explain entropy in the following way. So entropy is a measure of disorder in a large system. A large system is one which is made up of a large number of microscopic constituents. For example, a box of gas which has, a mole of gas, say 10 to the 23 particles, a large number of small microscopic constituents. And the disorder refers to the disorder in the arrangement of this microscopic constituents. So if you have a hot box of gas, then there's a lot of disorder because these atoms can be in lots of different positions. Whereas if you cool it down, then things become more ordered. Closed or isolated systems such as our universe tend to evolve towards more disordered states rather than less disordered ones. These microscopic constituents tend to mix up with each other, creating creating a more and more disordered state, right? So for example, if you take coffee, you put sugar in it, stir it, right? Now the sugar was neatly over here, the coffee was there, you got something which is more disordered. Spontaneously, like we have never seen the coffee unstir itself and the sugar come out. Right? Similarly with the air in this room, right? It's going all over the place, but at least we are not afraid that we are just going to die in the next second because all the oxygen in the room has decided to go and concentrate over there, right? So this tendency to never decrease disorder has the status of a law of physics, and it is called the second law of thermodynamics, and it states that physical process can never decrease the entropy of an isolated system. And entropy, once you know the microscopic constituents, you can calculate a number, and it doesn't ever decrease. Good. So what is this to do with black holes? Now, this is Feynman's advisor, John Wheeler. He became very interested in gravity in the 50s, right? There's a big gap. Actually, there's a wonderful history of GR, which again I can tell you after the talk if you want to know. And he and along with a few others that heralded a rebirth of gravity, called the golden age of gravity, of general relativity. And he had a bunch of students in Princeton, right? In fact, Wheeler graduated, I think, the maximum number of students from Princeton, around 42 or so, and many of them really brilliant chaps, right? So he had a student, his name was Bekenstein, and Wheeler asked Bekenstein, what happens when you throw, actually he said, a cup of tea. You take a cup of hot tea and you throw it into the black hole, then what happens? So what do you mean by this question? And Bekenstein was sharp enough to go on thinking about this more and more. What he meant was the following, right? If you take a cup of tea or a box of gas or any entropic object, you take it, you chuck it into the black hole, then in your observable universe, the entropy is decreased. So the question is, has the second law been violated or not? Because here clearly I've made a physical process and the entropy is decreased. So Bekenstein was quite worried about this. But what he noticed was that when you throw something into the black hole mass increases, the geometry settles down to a black hole of a slightly larger mass. And once the mass increases, it turns out that the area of that horizon, which I told you, also increases. So Bekenstein proposed that what should be really the entropy is a generalized entropy, where the black hole itself has an entropy. And he proposed that the black hole could have an entropy. So what did he do? Bekenstein has a series of papers where he keeps on chucking things into the black hole, right? And what he wants to do is to take the maximum entropic object he can think of with the minimum amount of mass, right? And chuck it into the black hole. And he found no matter what he did, if he ascribed to the black hole an entropy which is proportional to the area, and I'll tell you about the proportionality constant as well. If he did that, then he found that the initial area plus the entropy of the gas or whatever was always less than the final area without the gas which has fallen in. So a generalized second law of thermodynamics was fine, provided you could assign the black hole itself an entropy and assign actually its horizon an entropy, which is given by the area. And the proportionality constant he found was order 1 times the Planck area. Planck area was that same object we met, 10 to the minus 35 meters whole square will be the Planck area. So if you take the area of the black hole divided by the Planck area and then multiplied by Boltzmann's constant or something, then you get something which is of entropy, and it's huge, right? And this, all his thought experiments, he could never violate the increase in this generalized entropy. Okay? So now you find that suddenly, just through these thought experiments, the Planck area has appeared. Right? And you can then ask the question, okay, I know that entropy is something I should be able to calculate if I know what are the microscopic constituents of the system I'm looking at. And this is very strong. So the question is, what are the microscopic constituents, right, of this black hole or the black hole horizon, whose gives rise to this entropy? And because we have a factor of the Planck area, right, it almost suggests that we are counting a huge number of gravitational bits of Planck area, right? And if you sort of 2 to the n bits, etc., and if you do all the calculations, then you find that log of that actually comes out to be the so it's a very suggestive thing that perhaps what is responsible for the entropy of a black hole is something very, very quantum gravitational. All right. So this is again another reason, which is why, and this goes on, there is further, this is the second law. There are also analogs between the behavior of general relativistic solutions and the first law and the zeroth law. And then there is a puzzle, which is called the Hawking information loss puzzle. And again, I don't have time to tell you about it, but that is also a very interesting thing. Yeah, if there, go ahead. Yes, yes. 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 So it is approach dependent, right? Different. So it depends. So again, no. So what? Oh, yeah. It's a good question. The point, all I'm trying to do at this point is to say that this is deeply suggestive of the fact that somewhere in this story of black hole entropy, gravity is involved. And remember, what we are discussing right now is why a physicist is not considered insane if he's studying quantum gravity. So I'm trying to give you arguments as to why you would not consider someone like me completely insane. Okay. So now, of course, once you buy this, then what is exactly your quantum gravitational degrees of freedom? What is the density matrix? What happens? Those are legitimate questions, and the answers will depend on the approach you take to the problem of quantum gravity. Yes, yes, yes. That is a different, that is something different. So let's not mix up too many things, because even let's postpone that discussion, because there are no clear answers. I mean, even in normal systems, right? I mean, this is a puzzle, right? I mean, the ergodic hypothesis need not be true. Then there are other ways in which you. So one goes to foundations of statistical mechanics. Those are the kinds of questions you're asking, which are equally valid for ordinary systems, right? But if one is agnostic about that and just looks for degrees of freedom, tries to count microscopic constituents, there's something over here which will be responsible for that. And it seems like some quantum gravity theory should play a role in that. The questions you are asking can be asked also at the level just of foundational statistical mechanics of anything, right? So that we can take later, and we can. And I don't know. I mean, Boltzmann killed himself because he couldn't. He tried to answer them and he couldn't answer them, right? And so it's like a bad end if we try to. I'm just joking, okay? But yeah, yeah. I mean, you guys know this, right? Boltzmann was obsessed with this whole thing about entropy and foundations, etc., and how things, irreversibility, and so on. And finally, he got depressed. He thought he never had the answer, and I don't know how. But basically, that was the end of Boltzmann. Okay, so just to summarize, up to this point, GR is incomplete, right? It's an incomplete theory because of singularities. And in fact, one may think these are very special solutions, but Penrose got his Nobel Prize in 2020 because he showed that in some sense, singularities were not so special. And if I had time, one more day or something, I could tell you about Penrose's singularity theorem, for which he got the Nobel Prize, which is a beautiful example of completely new techniques which Penrose brought into the field, but which we can even understand at some level in terms of geometry, etc. And Professor Roy Chaudhary, Amal Roy Chaudhary, plays a important conceptual role in this. Not, and Penrose did it without knowing of his work, but his equation. I mean, the general community have named an equation which is even more general than in the particular cases Roy Chaudhary proved it. And so there is a very interesting and nice story about all these things. And another big hero like P.C. Vaidya is also involved in this whole business of black holes and finding solutions and so on. So there is a tremendous Indian contribution. And actually, just as a historical aside, people often wonder why it stopped. I mean, with so many wonderful people in the Calcutta school, why did it not nucleate, and grow to something enormous when it could have been the case? Anyway, secondly, there's a mysterious connection between completely disparate fields, right? General relativity and statistical mechanics of thermodynamics. And this suggests that black hole is an entropy. Can quantum gravity provide an understanding of the origin of entropy? So these are two reasons why a theorist like me would like to study quantum gravity. Okay, let me now go to quantum gravity and observations. I'm not very conscious about the time, so I mean, but I don't have to finish something. I can just go and stop at some point. You see, no direct experiments are possible at the Planck scale, right? That we've already convinced ourselves of. But is there any other way in which to make quantum gravity and observations talk to each other? There are two sets of relevant observations. One I will not discuss now. You can ask me later. Local Lorentz invariance and its violations. Are there any violations? And the second is early universe cosmology, right? The universe as a laboratory. Can we glean something from there? Learn about quantum gravity. Now, let me focus on cosmology. As we discussed earlier, our universe started at the Big Bang. That's when space and time were created, at least according to classical GR. But one expects near the Big Bang that there would be strong quantum gravitational effects. If there were strong quantum gravitational effects which affected the dynamics right, at the epoch close to the Big Bang, is there any way we can see effects of these effects now? Okay, that is the question, right? Now it seems impossible, right? Because we are billions of years away from the Big Bang. I mean, how could we? So many things have happened, even between day before yesterday and today. So if we go back billions of years, I mean, what memory are we going to have of these effects? And however, it turns out that if we are lucky, then the peculiar evolution of our universe might be able to allow this. Okay, so we don't know for sure, but it might be possible that this can happen. So very briefly, how does that happen? As I said, the universe at large scales looks very uniform. Unless the universe was itself born in a very special uniform state at the Big Bang, it's very hard to see how this can happen. Why? Because different parts of the universe here and there, which we look at today, would have to interact with each other and homogenize. And now, the larger is the region of homogeneity, obviously, the more time is needed for these different patches to interact and homogenize. Now, for the large patch of homogeneity which we observe today, right, if we go back to the Big Bang, which is a finite time away, you find that there was simply not enough time for this large patch to have homogenized. All right? And therefore, what people do is that they propose something else. And that something else is called inflation. So if what happened was that the large patch we are looking today actually really came a long time ago from a small patch which had homogenized, we would be okay. So what you need is a period where a small, very small patch very rapidly expands and becomes huge, right? And then we can perhaps explain large scale homogeneity which we see. And that rapid phase of expansion is called inflation. Okay, so within, like, I don't know, 10 to the minus 33 seconds or so, the universe just like expands by, factor of, I don't know, 27 or exponentially, so it's huge. It's just like unimaginably huge. And this is what physicists have proposed as one solution to cure this problem. Now, but therein lies an opportunity, because something very small has very rapidly inflated. And it turns out that if you have just the right amount of inflation, because of this, when you put everything together, it turns out that the larger scale features we can see today might have arisen from Planck scale features very long ago. Thus, early universe Planck scale physics might imprint on large scale features of the cosmic microwave background radiation, which is our probe of what the universe looked like 300,000 years ago. Okay, so I know I haven't told you why this happens, but at least I've told you that inflation offers you a paradigm whereby very small can be linked to very big, right? And so maybe if you do something at the very small, you might see it today in the very big. Okay, so that is a rough idea over here. Let me now just go back and to approaches to quantum gravity. They fall into two rough classes. One is deriving from a particle physics way of thinking, and that is the dominant approach, which today is called string theory. And then there is the community of general relativists who thought about the problem, for whom space-time geometry was the most important thing. And out of that has come various things like loop quantum gravity, Regge calculus, causal sets, causal dynamical triangulations, etc. And then there are some things which lie in the middle, which is Hawking's Euclidean gravity, and a very interesting approach called asymptotic safety. For those who know about fixed points, this is actually was proposed by Weinberg a long time ago, where he proposed that there might be, for the gravitational interaction, a non-trivial fixed point, not the Gaussian fixed point, but some non-trivial fixed point which will keep the theory safe in the ultraviolet. And people are trying to work on that assumption and provide proof for it, and so on and so forth. So I work within the loop quantum gravity approach, And the aim over here is not to unify all interactions. It's not as an ambitious program as string theory, but rather to understand the new physics which may arise when one tries to combine the principles of quantum mechanics and gravity. Because we already saw that things can go completely haywire, right? And are there any robust consequences of this merging of quantum mechanics and just space-time geometry? Can we get something out from this? That is the modest. It's not so modest. It's quite a big goal, but can we at least try and do that? So let me say a little bit about loop quantum gravity, and then I'll close the talk. So let's first look at a quantum mechanical system, right? Just a usual particle, right? Particle in a box or oscillator or whatever, right? So it has a position q and it has a momentum, right? Mass times the velocity. So what happens in quantum mechanics? What do? We can think of it as something which happens in two steps mathematically. First, we have q and p, and we turn them into operators which act on some space of wave functions, and which are subject to the q and p operators are subject to Heisenberg's uncertainty principle, right? So that is just the what I would call the kinematics of the system, right? Where you have uncertainties, you have wave functions, and you have a representation in terms of operators on some what we call a Hilbert space. However, that is not enough. Now you have to tell me what dynamical evolution is. So we know that the wave function evolves in time with the Schrodinger equation, right? And so those are the two elements of quantum mechanics in terms of its mathematical structure. In gravity, what is the analog of Q? It turns out the analog of Q is just the geometry of space at a fixed time. Okay, the geometry of all space at a fixed time. So what is the spatial metric at a fixed time? That is like the Q. And Q dot, which is, remember, Q dot was the d by dt of Q was like P. Here also d by dt of Q is like P, but it has a nice geometric interpretation of, if you have your space-time and you look at an instant of time, you have a slice of space-time, and how this slice curves in the ambient space-time. A measure of that is called extrinsic curvature, and it turns out that the p variable has the geometrical interpretation of extrinsic curvature. Now, of course, spatial geometry is defined everywhere, right? So you don't have one Q and P. In effect, you have a whole infinite set of Q and P's at every point. And in other words, this is a field theory of quantum mechanics. And this, of course, makes things complicated. Now, it turns out that LQG finds a nice way to turn certain functions of these Q's and P's into operators which are subject to quantum uncertainties and which do act on wave functions, right? So that is feature one, which we have well under control. However, feature two, which is a satisfactory construction of the very complicated Schrodinger equation appropriate to gravity, is still open, though there has been much recent progress. And in fact, this is where most of my research over my career has concentrated. However, what one can still do, right? So this is foundational mathematical physics, and trying to make sense of all these things. There are also a lot of difficult conceptual questions involved. However, what can one do? So there has been a lot of progress till now. We don't have the final solutions to anything. We're very far away. But what one can do is look at what has been developed, the ideas which have been developed, and apply those ideas of LQG to simpler situations where we believe that there is a certain physical situation in which the dominant physics is described by only a few modes of the gravitational field, not the gravitational field in all its glory, right? So if we assume that there are these situations, so one situation might be exactly cosmology, where it seems that the homogeneous and isotropic modes of the gravitational field are really what is controlling most of the physics. So let us make that assumption, and we look at a quantum theory now of gravitational fields which are homogeneous and isotropic. In particular, since they are homogeneous, they don't depend, the gravitational field here and here and here are not different, they are all the same. And therefore, the infinite number of degrees of freedom are now finite, and you do have quantum mechanics, but you choose the representations which are using, you choose the way in which dynamics happens, looking at whatever you have done in full theory of quantum gravity, which is, right? So whatever partial results you have in loop quantum gravity, you feed into quantization of this simpler system of few degrees of freedom. Now, yes, can, yeah, I'll maybe we can finish because I might be running out of time, and then I can take your question. Now, so that so in the early universe, gravitational physics, that's what I said, it's homogeneous. Another example is if one is only trying to understand black holes, we want to understand the singularity, this, that, and the other. Let us just concentrate on spherically symmetric black holes, just to start out with. And then again, switch off all non-spherically symmetric modes and see whether we can make some progress. Now, applications, now both in both these cases, in the Big Bang case and in the center of a black hole, you have singularity, right? And remember, one of our early questions was, do quantum effects in gravity resolve the singularities of the classical theory? Applications of LQG ideas to these physical situations hint at the tantalizing possibility of singularity resolution. So, due to strong LQG effects near the classically singular region, a strong, really totally quantum gravitational origin repulsive force manifests, which prevents collapse to singularity. This is what people have found when they've studied these simpler model systems using techniques from the full theory. So instead of the Big Bang, you get a big bounce because suddenly there's this repulsive force which is for a very short duration there, and it just bounces. Rather, the universe doesn't collapse, but it starts expanding again. So there is a collapsing branch which then goes into our branch, which is now an expanding branch. Inside a black hole, where the central singularity is, that may be resolved and it may lead to a vast new region of space-time. And this has something to do with what I couldn't discuss today, which is an alleviation of the Hawking information loss problem. Okay, so while such applications of LQG ideas open up fascinating possibilities, they also then provide input to its foundations. So somebody like me say, oh, this is a physical thing, it's interesting. Maybe can I take that back and try and put in the mathematics of that into my theory? Because I could make progress in this simple setting and it's physically interesting. Maybe I can feed that back into the foundation work, make progress in foundations, get some nice structures. Maybe I can use those to try and modify my quantum treatment in this. So there is a feedback between these two. And that's all you can hope for because of the paucity of experiments in this field. Okay, so let me conclude, I think. Maybe it has just decided. Okay. So in conclusion, quantum gravity, I hope to have convinced you, is a fascinating subject with deep conceptual implications. In fact, that perhaps is, one of the things which I didn't say, right? I mean, if you had a theory of quantum gravity, then I think the consensus is that absolutely it would be paradigm changing, right? Just like quantum mechanics, of course, solves various problems as all of you in this building are trying to solve. But conceptually, it just gives you a completely new paradigm, a new way of thinking about things, which classical mechanics simply didn't have. So quantum gravity is bound to be something completely different. Maybe it will involve modifications of quantum mechanics itself as we understand it, not only the gravity side. The one thing I want you to take away from this talk, if nothing else, is that quantum gravity is really the quantum mechanics of space-time itself, rather than quantum mechanics within space-time. While direct experiments at the Planck scale are impossible, perhaps in recent times, I would say it's too bold to say experiment quantum gravity, but that desperation of theorists to make some contact with observations might be seeing the beginnings of some fruit. There are tests of local Lorentz invariants, which I haven't gotten into. The hope that precision cosmology is a probe of physics of the early universe. And there is even a tabletop experiments, with gravitationally mediated quantum entanglement, which people have proposed, right? Which in the future, which do seem within reach, at some future stage, where one may learn something about the quantum nature of the gravitational interaction. Perhaps yes, perhaps not. So I think perhaps that is all I wanted to say, and I would conclude at this point. And if you have questions, or if you want to learn about this, my hero in all this thing, the guy who discovered the first solution to Einstein equations, I'll be happy to tell you. Thank you very much. Yes.
When you discuss the loop quantum gravity, then so introduce some geometry to discuss PQ.
Yeah.
So will it change also the commutation relation?
So the idea is that so the idea of and when I talk about loop quantum gravity, perhaps you to put in front of it the word canonical, because many people are doing something else which is also called loop quantum gravity. I mean canonical, which means Hamiltonian loop quantum gravity. No, so in a Hamiltonian, so we are trying to be conservative, right? And we are trying to see what is it that has worked when one tries to write down a quantum theory for other systems, right? And there, what is the way one proceeds is that there is a classical Poisson bracket structure, and we want to represent that structure in terms of operator commutation relations. So that is a step which chooses for you what is the right representation, or what is the right class of representations of your theory.
So, so you don't consider the fact that when you go to Planck length scale,
yes,
then the commutation relation changes.
I mean, who knows, right?
I mean, there are a
right?
lot of works. I mean, people do experiment actually when they try to detect this, let's say, this modification.
Right.
Using some, let's say, quantum optical experiment, tabletop experiment.
So then it's a bit of a, you see, there is also a step as to how one goes from the fundamental quantum theory to what your observable things are now, right? And there, I don't know, in that passage, it could be that a number of different things happen, which might, right, the basic mathematical commutation relations of classical theory are taken care of, but what comes out effectively from the theory and what you measure, these are slightly different questions, right? But nevertheless, if you are asking from a basic standpoint, a basic prejudice of the approach, right, then it is that whatever are the classical commutation relations, just like we do for other theories, we are going to represent them mathematically in terms of this is the starting prejudice. I want to say a couple of things, right? You see, when Einstein found his general theory of relativity, right, he wrote down these nonlinear coupled partial differential equations. It took him 10 years, 12 years, 15 years. He got stuck, this, that, and the other, and he finally had these equations, right? Now, these are just some coupled horrible nonlinear equations, very difficult to find solutions, right? But nevertheless, they have, in the years which followed, amazing properties. And one amazing property they have is that you can define a well-defined, they admit what is called a well-defined initial value formulation. So if you give me data, which is exactly this metric and the extrinsic curvature, right, which is of some smoothness class or whatever, you can show that when you evolve this data, you can evolve it in a certain technical sense uniquely and get and this was not at all guaranteed, right? And it need not have happened. Another beautiful thing which happens is that you see, you can look at these as kind of quasi hyperbolic equations, right? And over there, if there's this whole study of characteristics and so on in differential equations, and you can show that basically this thing, which is that the velocity of light, nothing can exceed it, has a very, it tells you that the characteristic curves of the differential equation have to behave in a certain way, right? And that also is true. Then you may also wonder, gravity is attractive, right? And Newtonian gravity is attractive. So, it might be that, for example, if you have a notion of energy in gravity, which is very subtle, maybe, you don't have a positive energy theorem. And it took until the 80s to actually show that no. For isolated systems with gravitational fields, the total energy is always positive. There is a theorem, the equations, if you have positive energy matter, of course, if I give you matter itself, which has negative mass, then I can't say anything. But if matter itself is of positive energy, then it is these Einstein equations which tell you that the total energy, the total mass, is called the ADM mass, is always positive. So I'm just saying that for a general relativist, there are unknown and extremely beautiful consequences of the Einstein equations themselves, which is why a general relativist accords, beyond the physical testing and so on, some special status to the Einstein equations. So if you meddle with them, nobody knows which of these properties may go away. Maybe you don't have an initial value problem. Certainly, if you put higher curvature terms, you can have superluminal propagation. The characteristics are not only along light rays. Positive energy goes out of the window. So many things which are beautiful about Einstein equations they are really wonderful things which Einstein could never have himself predicted. And so if we take a lot of guidance from the classical theory, we take it because we believe that it is such a beautiful, unique theory that maybe it's a good starting point. Now, maybe we may be wrong, right? We just don't know. Yes, yes. No question is naive. You know as much about quantum gravity as I do because nobody knows anything.
This is when you add mass to the black hole.
Yeah.
But you're throwing coffee, whatever.
Yeah.
Does the density change or it remains constant?
Density of what?
Density of the black hole itself.
So that is so one doesn't. You see, the way a black hole is defined, right, is something which has a horizon. Okay, so it's a very geometrical concept,
Yeah.
and
I'm thinking in that light.
yes,
If the black hole is large,
yes,
horizon also would be large, right?
will be large. It'll have a large area.
Right. So now if I assume that when you add mass
Yes.
and if density remains constant,
So what happens?
then its size becomes bigger.
So what happens to the
horizon will
mass?
be
The
large.
mass goes in,
Hmm.
it falls in, and it goes into the central singularity. The
But-
black hole geometry adjusts, right? And because of the Einstein equations, the horizon area becomes large.
I'm just thinking in terms.
So there is no density. I mean, so it is.
If the density changes,
Yeah.
then I cannot linearly connect that the size is going to be larger.
Yeah. So I think it's an inapplicable concept as you formulated it, because really this is just space-time geometry.
Okay.
There is nothing tangible about about a density, etc. Having said that, people like I think Richard Price and somebody else, they actually tried to look at the horizon as a physical membrane. So it is called, there's a book called the membrane paradigm. And by looking at certain geometrical properties, they were able to map it to physical properties which we are familiar with, like viscosity and pressure and so on. And I don't know whether in that sense there could be some contact with the kind of things you are trying to ascribe the horizon of a black hole. So I don't know because I have not read the black hole membrane paradigm. So there it is an analogy of if you do something to the black hole in a certain way, it behaves like a viscous membrane, it behaves like something with this, it has tension. So those things, there is a map between those things and the familiar things of a fluid which we understand. In that sense, maybe there is some ascribed density you can assign the black hole horizon. I don't know. It's something which I would have to look at.
The second one is
Yes.
related to your homogeneity and inflation.
Yes,
You said a small patch
yes,
probably has undergone rapid inflation
yes,
and it become homogeneous.
yes,
So then there must be other patches.
yes.
So they are not homogeneous yet.
I mean,
They have not.
so you
they
have,
not undergone high inflation.
well, the whole universe undergoes inflation, right? So
Yeah, but
that is
You also give an example of some patches.
right.
might
So
be
people
more-
talk about these cosmological bubbles and multiverses where, we are only one of these possible multiverses which are each evolving in different ways. But I I don't know much about this. But in the inflationary paradigm, there is room. I don't know for exactly what you're saying, but certainly uh, conceptually, what you're saying is correct. I mean, I think there are, if there are cosmologists in the audience, maybe someone can say something more. But yes, we are concerned with our universe, but they can be what is called a multiverse, in which there are.
They may still be homogeneous now.
Um, that yeah, I don't know. I just don't know about this field because yeah, I don't know. I would rather be safe and say I don't know. I would have to read about it.
Okay, thank you.
Okay, I want to tell you before I come to you. I want to tell you one story before you go. Okay, this is nothing to do with physics, but it is so nice, and I learnt about it in a little bit of detail. So I want to have a captive audience and tell you this story because I find it really inspiring. So this guy who found the first solution, right, to Einstein's equations in a matter of 6 weeks after the equations came, he was actually an infantry lieutenant fighting on the Eastern Front in the First World War. Okay. Uh, and his story is pretty amazing. I'll just take another 3 minutes to tell you what the story is, right? So this guy, his name was Carl Schwarzschild, right? He was born into quite a happy family, and he was a very gifted physicist. Yeah, but he was a very, so before all this, already in his 20s, he was a world-renowned astronomer. So he had all, so, and he was a real, I mean, what you would call an experimentalist also. He went for Sizu or some other people. This technique using diffraction gratings in telescopes to separate close by images of stars and so on. He actually commissioned gratings, to telescope themselves, and he would also do theory, right? So he had, so it was around in 26 or so, this was 1901 or so, he was already sent to take over the observatory in Heidelberg as its director. And 1 year before this, this was in 1900. Okay, so that special relativity came in 1905, general came in 1915. This guy in 1900, I don't know how, I've not read the paper, he estimated if the universe was a sphere, what would be its curvature? And if the universe was a hyperboloid, what would be its curvature? Okay, so it's already in 3 dimensions or 4 dimensions. This was in 1900. How the hell did he knew more differential geometry than Einstein knew in 1915. The reason this happened was that if you go back 50 years earlier, there's this great mathematician Gauss, okay, in Göttingen, who understood two-dimensional curvature very, very well, right? And he had a brilliant student, Riemann, who generalized his work to higher dimensions. And there is a lecture called, I think, on the foundations of geometry by Riemann in 1850, where he speculates that perhaps the geometry of space is curved and perhaps there is some physical reason for its curvature. And this strand of thinking was very much in vogue for 50 years later. And Schwarzschild evidently had been part of this whole thing. So he already knew differential geometry and so on and so forth. We go back to 1901 when he was director of Göttingen. In Göttingen itself, he met various luminaries like Minkowski and Hilbert and so on and so forth. Ehrenfurst came and did a course under him, Ehrenfurst, another guy who killed himself with quantum mechanics. And then at the age of 36 or so, he was a famous astronomer, and he was sent to the most prestigious post, which was to take over the observatory at Potsdam, right? 4 years later, it's 1914, and the First World War breaks out. And Schwarzschild is already 40 years of age. He has no need, he's not conscripted. He has no need to fight in the war, but out of a sense of patriotism, he goes and he enlists. So first he's sent, he's in France and then in Belgium, and there he's put in the artillery regiment, So he's not actually fighting, but he's right at the front and he's computing trajectories of artillery shells and so on. And then finally he's sent to the Eastern Front, right? And there are trenches, there's warfare, and he's right over there, even though he's not fighting, right? And bullets and this thing and all are whizzing by. And somehow he has a contact with Berlin. And in 1915, which is 1 year after the war starts, he gets in mint condition Einstein's theory of GR, right? His lecture in Berlin Academy or what comes over there. And Schwarzschild looks at it. And of course, since he knows all the differential geometry, um, even Einstein couldn't succeed in solving his own equation. Within like a matter of a few weeks, he had what is called the Schwarzschild solution, which is the first solution which happens to describe the exterior of a black hole. Now, not only were there, and he writes to Einstein, he says that as you can, as you can see, when he sends the solution, he says, as you can see, the war has been kind to me, right? Even in the midst of bullets and so on at near quarters, I'm still able to walk in the land of your beautiful ideas. So there's a letter from Schwarzschild to Einstein. Not only was he in the middle of this war, he also was suffering from an autoimmune disease where the skin started eating itself. So he was an Ashkenazi Jew, and apparently due to the close gene pool, this afflicted that community more than others. And so he was dying. Okay, so he was dying. He was in the war. He was still cheerful, and he wrote not one paper, but 3 papers, 3 amazing papers. He wrote this paper on the exterior Schwarzschild solution. He wrote another paper where he computed, I think it was for dust or something like that, where he computed some solution. And then he wrote a third paper, right, where he computed the start effect using Bohr-Sommerfeld rule. I have not read that paper. So the guy knew like astronomy, he knew telescopes, he knew GR, he knew quantum mechanics, and he was like happy and cheerful and war going on, dying, whatever, and he writes these 3 beautiful papers and then he gets discharged and he dies. So whenever, I complain that the coffee is cold or, something is, then I remember this guy and then I said there is no room. Sorry. I wanted to tell this story because I find it extremely, maybe the students also would, I find it very, very inspiring that, that such a man existed and that he did such seminal work. Sorry, now the captive audience is free to, to disperse. Right. No, I mean, there are 2 documentaries one on which you may have seen, one on Professor Roy Chaudhary and one on Professor P.C. Vaidya. Both used to come for these GR meetings. I never had the courage to go and talk to them. But P.C. Vaidya's story is also incredible. I don't want to burden you with too many stories, but if there is interest, I'll tell you that story later. Yeah, don't hesitate, please. I mean, yeah. I know I dragged you back into your seat, but sorry. Leave happily. Thank you. Yeah, go ahead. You had a question?
Question was,
Yeah, I'll tell you. It was a fascinating.
so my question was in LQG,
Yeah.
you said that there is a Schrodinger equation.
Yes.
So in principle, Schrodinger equation is a kind of an experimental equation. You have an
No, so actually the situation is much more complicated.
So here
Because in gravity, so why is it so difficult, and why is even LQG, why did it take so long? Why is it so difficult, right? The point is that you don't, in any quantum theory you write down, for example, in quantum mechanics, right? You have a sense of time,
yeah,
right? There is this Newtonian time, absolute time, which is there. If you're doing it in flat space-time, you have flat space-time there. But now you have nothing, right? Because there is no, you cannot say that there is a particular space-time which you're using to quantize space-time. There is no space-time. So that is what makes it much more difficult. And in fact, the Hamiltonian formulation of gravity itself, classical gravity itself, is very subtle.
yeah.
Because when you say dynamics, your dynamics with respect to what? There is no pre-existing time. The time is generated from the dynamics itself. So that is the, so it's a bit of a simplification to say, I just said it uh, in the sense of kinematics versus dynamics, and that is still true, right? But this is called the problem of time. So, so yeah, there is a much bigger story to tell about that. So you see, so each approach, I mean, string theory also offers a explanation of black hole entropy. Right, right. So not for realistic black holes, but so I would say in LQG the situation doesn't require supersymmetry, right? And what you can do is you can tell your phase space classically that there is a black hole by a certain boundary condition. Okay, that tells you that there is a black hole, and you can impose this boundary condition quantum mechanically, right? And you can look at the number of possible solutions to this boundary condition, and you can count them. And in a certain precise sense, they scale as the area of the horizon. Yeah, so those are, because in LQG the actually the area is quantized. The area, it comes not an input, but it comes out of the theory that the area of any surface comes in it has a discrete spectrum, and so you can count. So that is the heart of the counting thing. And in fact, one of my friends, Fernando, he did an exhaustive analysis. He's like Mr. Asymptotics, and he quotes. If you ask him to give him a talk tomorrow, he will quote Brahmagupta. in his, in some of these what are they called, those equations which integer solutions, Diophantine equation. You get a Diophantine equation, you have to count the solution. So PC Vaidya. PC Vaidya, this is all from the documentary, a fascinating fellow. He actually he came from a small town in Gujarat, right, Junagadh district. And he was very interested in math and physics. So he got his bachelor's degrees partly in Gujarat, and then he went to Bombay for a little bit. Then he came back, right? He was around in his early, and he got a job teaching in Rajkot, probably in that Rajkumar college, although I'm not sure.